We are going to get started. This session will be recorded. Hello, and welcome to Sterling and VMware's Power Block session. I am Megan Moore, Sterling's VMware Partner Business Manager. We know your time is valuable, so we want to say thank you for choosing to spend a portion of your day with Sterling and VMware. Before we dive into the demo, I wanted to give you a brief overview of Sterling's capabilities. Sterling is a principal VMware partner and a preferred services partner authorized to sell and service VMware solutions to customers across the nation. With 50 plus technical staff and 75 plus sales staff, all trained on VMware offerings, we are sure to provide you with an industry best value on all of your client to cloud IT needs. As you can see from this slide, Sterling holds many VMware competencies, including 2 master services competencies and more coming soon. Sterling offers complete customized solutions from client to cloud. We serve on multiple federal, state, and local government contracts and support all industry verticals. Security is of the utmost importance here at Sterling. We have a robust, secure supply chain, including OTIPs and CMMC certifications. For any questions about Sterling, please use the email aliases you will find at the end of the demo. For questions during the demo, please put them in the Q&A feature at the bottom of your screen, and we'll address them at the end. Now I will turn it over to Cloud Architect Billy Downing to demonstrate Tanzu security with NSX-T.
Awesome. Thank you, Megan. I appreciate that. Can you hear me okay? I've been having some audio issues lately.
Yep, you sound great.
Okay, perfect. So thank you for the introduction. My name is Billy Downing. I'm a cloud architect here at Sterling on our strategic services team. And today what we're going to talk about is how to incorporate NSX-T into Kubernetes. We're going to use Tanzu as the Kubernetes platform of choice, but that by no means that is the limitation of NSX-T. But what we're going to start out with is just a quick level set of Kubernetes. I like to do a little analogy for what it is, just to kind of set the framework of why we're talking about Kubernetes in the first place and how that incorporates with VMware and vSphere. Then we'll talk about exactly what my topology in my lab looks like and how that Tanzu aspect or that Kubernetes aspect is integrated into VMware Cloud Foundation specifically. Then we'll explain a little bit like what is NSX-T, just from a high level, what is it and what service is it providing for us in this context. And then specifically some use cases and some specific metrics of how NSX-T directly integrates with Kubernetes using the NSX-T container plugin. And then I'll go through a demonstration and show you the UI of my VCF environment or VMware Cloud Foundation environment, NSX-T, what that looks like. And then we'll take a look at it from a Kubernetes perspective and deploy some network policies for some applications that I have running on top of NSX-T, just to show you what that would look like if you were to deploy something like this in your environment. And feel free, like Megan said, to ask questions as we go along. This is all a live environment, so if there's anything you'd like to see or anything like that, just go ahead and let us know. So for starters, I like to do a Kubernetes analogy. And so what I'm equating this to is imagine that you're going to a store. Your end goal is to go to some sort of a potluck or a white elephant party. And your goal is to buy a bunch of different gifts for a bunch of different people. So they all have their own purpose, but they're all for the same event. So you start off with going to a store, you buy a bunch of gifts. The store puts all those gifts and they wrap them into a single large package for you to take to your event. So you have all of your gifts, they're all in one single package. The difficulty now is that you get to this event, but you want people to be able to open their gifts individually. You want each one of these gifts to be treated as individual gifts, just so happen to be given out at the same event. So what you do is you take them out of that package and then you wrap all of those gifts independently. So now you have, 5 or 6 individual gifts you can go around and hand out at your potluck or your white elephant party. So you've solved one problem, but you've kind of created another. And when you decoupled those gifts from that single package, now you have the issue of now you have a bunch of gifts to kind of manage and, where do you put those? Do you just hold them all, that kind of stuff? So you have more of an overhead issue now. So the last thing to solve that final problem is to get less than a single package for everything, but now you're kind of providing a platform for it. So say you bring a loose bag, or you find a table there that can act as a platform for all of the gifts, as you would see commonly at some sort of a potluck or a white elephant party. So you kind of solve that last problem. So now you end up at this place where you have all of your individual gifts. They're treated like individual entities. They can be handed out independently of one another, but they share this common platform to organize them all together. So everyone knows that platform is where those gifts are placed. So when I want to handle my gift, I go and grab it from there. So how does that relate to Kubernetes? So if we start from left to right, we'll basically go through and explain that first initial idea there when you're purchasing those gifts, and they're all coupled by the exact same package. That is the idea of a monolithic application. So that would mean you have a virtual machine, a single virtual machine that's hosting all the different processes that actually are used within your application. And what that means is everything is tightly coupled. All of the packaging must accommodate every process that you have within your application, and they all must be supported by the same infrastructure. Obviously, this has worked very well, and this is not something, this is not me saying that this is no longer a way to do things. This is a certain design avenue. But for some applications, this can pose an issue to require all of your different processes to be contained in a very strict, there's very strict confines of a single compute entity. So what's the latest craze today is, or more recently in the last 10 years, is to break out all of those individual processes that were deployed on your virtual machine or your bare metal node, break out each one of those processes into containers. And now you have a decoupled application. So you have, you can refer to this as microservices architecture. And what this gives you is the ability to individually treat each one of those processes that made up your application as they are, as independent entities that can be developed in different languages that are most suited for the purpose of that container. And whatever the case may be, if they're on different upgrade paths, you want to make sure that one container doesn't die and bring down the entire application. But what you get there is just like that gift analogy is now you have this problem of maybe you had 100 processes for a single application. Now you're managing 100 individual containers across a distributed architecture. So you have hundreds of containers distributed across multiple compute nodes or hardware nodes. And so you get into this overhead problem where, okay, great, I have all these containers, everything is independent, they're networked together, everything is working, but I don't really have a means to lifecycle or orchestrate the planning or scheduling of all these different containers. So that's where Kubernetes comes in. Kubernetes provides that platform that you can deploy those containers on top of. So then you have that management and orchestration level for all those different containers. So you end up very similar to the gift analogy. You end up having this platform or this place where your applications can live. Kubernetes will orchestrate the scheduling for the compute nodes, and it'll integrate with different solutions to provide compute, storage, and networking. So what we're going to focus on here is how Kubernetes in itself is an orchestration engine. It's an orchestration platform, but it doesn't do all of the granular details of all the different aspects that are required by applications today. So how they've solved that problem is Kubernetes is really good at one thing, that's orchestrating and finding a desired state for your application. So what it does now is we have certain plugins that allow us to integrate with other solutions that also do a few things really well as well. So for instance, we're going to be focusing on the container network interface, and that's how Kubernetes integrates with different network solutions for containerized applications. And more specifically, we'll be talking about how Kubernetes uses that network interface to interact with NSX, to provide a singular fabric for your entire data center, bare metal, virtual machine containers, to provide that networking service overlay. So we talked about Kubernetes, kind of what it is generally, and just to highlight that, Kubernetes is a orchestration tool for containerized applications. It's that high level layer of management that allows you to schedule efficiently and lifecycle manage your pods, as well as giving them a desired state-based configuration. So let's take a look at what that looks like in a VMware Cloud Foundation type of infrastructure. So what I have here is the base layer. I'm using VMware Cloud Foundation on Vxtra. However, that is not a requirement to run Kubernetes on VMware. Obviously, you can run whatever distro you'd like, or you can run Tanzu, and that will be directly integrated with out of the box, directly integrated with vSphere. You can also do vSphere with Tanzu without the need of NSX-T and vSAN and all that stuff as well. But the focus here today is going to be that use case that involves NSX-T specifically, and how you're going to use that for visibility into your pods and how to secure your pods in your infrastructure. So anyways, we have this base layer. We have the management layer for our physical infrastructure. That's going to be the SDDC manager. And in my case, I have a VxRail manager as well. And the next step is all the different components that are going to actually orchestrate your workloads. So looking towards the bottom here, we have a few different management control plane objects. We have our vCenter, which you're probably all very familiar with. vCenter is what we're using in a virtualized appliance. We're using that to manage our ESXi nodes to schedule and plan virtual machine workloads. So that's what we're using as that orchestration layer for compute and how it's orchestrating vSphere across all of our hardware assets. Then we have vSAN. That's going to be our distributed storage. Again, this isn't a requirement. You can still use other storage vendors with VMware, vSphere with Tanzu, but vSAN is what we're dealing with VCF. Finally, we have NSX-T. That's going to be our software-defined networking aspect, and that's what's going to integrate with Kubernetes as well as vCenter to provide a single fabric for all of our workloads. And that can be virtual machines. We can incorporate bare metal instances into this fabric, and we can also obviously integrate Kubernetes and provide network overlays and services for our pods. And finally, to the left here, this is kind of the bread and butter of what vSphere with Tanzu is made up of. And this is going to be our Kubernetes control plane. So very similar to how vCenter is a virtual appliance that is managing our physical ESXi hosts to schedule virtual machine workloads, our Kubernetes masters are going to be virtual machines that are using our ESXi hosts as worker nodes to schedule pods and schedule guest clusters as well using the open source project Cluster API. So we have our management tier, we have our Kubernetes control plane with our 3 masters, we have our network fabric with NSX-T, our storage fabric with vSAN, and then our compute management fabric with vCenter. One layer up above that, we have our physical hosts. So we have our ESXi hosts here. I have them labeled as Kubernetes worker nodes because from the perspective of the Kubernetes masters, that is actually what is running. We are running a VMware version of Kubelet on top of these ESXi hosts so that your Kubernetes masters and those manifests that you create can actually be realized on those hosts. These hosts are running, I mean, as you know, ESXi is not Linux. So when we run, we have different ways of deploying pods on top of ESXi. We can do what I have here, which is called the vSphere pod. So the vSphere pod service, where you have essentially a Linux container that is running in a special CRX runtime, so a container runtime on top of ESXi to run those pods natively on bare metal as highly efficient. They essentially look like virtual machines from the perspective of ESXi, but they're running a very specialized and efficient kernel that is basically used to give you a shim between your ESXi host layer operating system and be able to present that pod the Linux kernel that it requires to run. So this is just a description of what CRX is. CRX is VMware's container runtime. So you can think of that as like Containerd or Docker. This is what is actually running and managing the containers on the bare metal hosts themselves. And they're going to be realized as vSphere pods. The highlight here is that you can run vSphere pods directly alongside virtual machines. So if you're in some sort of environment where you're just experimenting with migrating over to Kubernetes, or you want to run legacy applications, or not necessarily legacy, but some applications with virtual machines and some as containers, that's something you can do here in a shared namespace or a shared network type platform. So that could be something where you have all of your stateless applications, your web front applications are running on vSphere pods, and they're interacting perhaps with a stateful database that you're working in a virtual machine, and you're preparing to migrate that into Kubernetes, or you can keep it as a virtual machine. The whole point here is the platform allows you to do both. However, running these vSphere native pods on top of ESXi hosts directly using CRX is not necessarily a CNCF conformant distribution of Kubernetes. This is going to be a little more VMware proprietary. So if you have those needs to run in a CNCF compliant Kubernetes cluster, that's where you use TKG or that Tanzu Kubernetes grid service. So this is going to all use the same exact control plane that we've talked about previously, but it's essentially using Kubernetes to provision Kubernetes. So what we're going to end up doing here is in those same namespaces, our Kubernetes masters using Cluster API is going to actually provision and manage virtual machines that are working as Kubernetes master nodes and Kubernetes worker nodes, or control plane nodes and agent nodes rather. So what that means is now you have the opportunity to run vSphere, or not vSphere, but Linux native pods. You don't have to worry about any sort of proprietary information that deals with CRX or the kubelet that's running on ESXi. You have a completely virtual cluster that's still managed by the same confines of everything else in your environment. So it's still managed by those supervisor cluster Kubernetes masters here at the bottom. It's still using NSX-T for networking for ingress and egress traffic, and vSAN for storage, and vCenter to actually ensure that those compute nodes are where they need to be. So what you end up here is a platform that allows you to kind of do whatever it is that you need. You can run vSphere native pods alongside your virtual machines, or you can run dedicated virtual clusters. Wherever you are in that journey to developing cloud native applications using microservices and containers, this platform is kind of just there to support wherever you are in that journey, and you pick up where you are and start using the tools that are available to you. So that's just a little bit about the foundation that I'm working with here in this lab. So we'll take a look at what that actually means when we jump into the UI, just to explain this a little more, but I wanted to ensure that we level set that. So next, the focus of this talk is really, now that we have the foundation of how these tools are put together and what's managing what, a little bit about NSX-T and more so of how it's actually built and what we're deploying it here, how we're deploying it here. So NSX-T, and I'm going in kind of a clockwise motion here, starting from control and management. NSX-T at a high level is a software-defined networking fabric. So essentially the point here is that each one of your compute nodes, your ESXi hosts or Linux hosts, if that's what you're using, can be placed into a data center fabric and installed with network services such as routing, switching, load balancing, and things like that. So this essentially creates an overlay network topology that is managed by a central controller. So we have a central controller cluster that is going to manage all of our compute nodes and institute all of those different network frameworks and network services inside of those hosts themselves. So what that means is our top of rack switches, our physical switches, can be very simple in how they're configured because we're not putting any advanced services in our top of rack switch. So we're not having to run VXLAN or BGP with EVPN. If you're a network engineer out there and you hear all those terms, you don't have to do the complexity of worrying about ingress egress points with VRRP and all those different aspects. You're able to put all of that complexity down into your software layer on top of your ESXi hosts and manage that through NSX-T. So NSX-T is a software-defined centralized control plane that's made up of virtual machines deployed on the infrastructure. And then we have our data plane, and our data plane in this instance is our actual transport nodes, which are the actual ESXi hosts that it is deployed on top of. So all of those different security policies and everything like that is going to actually be running as VIBs inside of our ESXi hosts, so that to actually for our containers and our VMs and things like that to inherit the benefits of perhaps our security infrastructure, all that is built into the host itself. So as we scale out hosts, for example, we're also scaling out our network capability. So it kind of also alleviates you from that bottleneck aspect of perhaps you have a single firewall that is somewhere in your environment and you have to hairpin traffic through. Your bottleneck as you scale out compute becomes that firewall. So you now have to scale out the firewall. And if anybody has ever scaled out stateful firewalls, that's not exactly a trivial task. So speaking of which, for the security framework of NSX-T, because NSX-T is integrated directly into the compute nodes where your applications live, it's able to inject itself directly into those paths and place policy on the VM NIC of the pod or virtual machine themselves. So I have here a couple of those security policies or security capabilities. East-west distributed firewall. That is basically allowing each one of your pods to have a little firewall that's on the actual NIC. So as it exits that pod, it's actually going through a firewall policy that's managed by NSX-T. And it's doing that without having to hairpin or reroute traffic out to an external device or external policy engine like a firewall or an IPS IDS. It's doing that in the actual host itself that the application is running on directly. There are other tools that you can utilize with this, and we can talk about those briefly, such as IDS IPS or URL inspection. Also, something like a web access firewall if you're using something like an advanced load balancer with AVI or NSX ALB. Finally, what sort of services does NSX provide? So we know now that NSX is this overlay network fabric. It brings all these network functions outside of our physical network and into our software stack. So, we have our complete software stack at this point. We have our virtualization for compute. We have our virtualization for storage distributed across the host, and NSX-T provides that last piece of distributed networking across all of our hosts. So what services does it actually provide? So NSX-T provides security, obviously, through distributed firewall, as well as a gateway firewall for north-south traffic that's actually entering your fabric. It provides VPN connectivity if you have multiple Kubernetes clusters or multiple clusters spread across different environments, and that could be in the cloud or different on-premises environments. It will do NAT for your Kubernetes environment, as a lot of you know. When load balancing, or the service of type load balancer, going back to different pods, they're realized as endpoints. And oftentimes you don't want those endpoints, the actual pod IP addresses, to be exposed to the outside world. You want that gateway to only be through that load balancer. So your solution has to be able to do NAT or source-based NAT, so that any application that's accessing your pods are only aware of that egress facing or that outside facing IP address they can interact with. NSX-T also provides network overlay, routing and switching, and load balancing. So that network overlay is quite important with Kubernetes specifically, as a lot of you may know, is that one of the requirements for a network CNI or container network interface solution to cooperate with Kubernetes is that every pod has to be able to reach each other. So if you're in a data center and you have a best practices deployment where your physical top of rack switches, each rack is a layer 3 segmented area. So you're segmenting your layer 2 broadcast domains between racks. Then you don't have a layer 2 connectivity or layer 2 broadcast domain across racks. Therefore, you can't stretch subnets. So the traditional way of doing that today is to deploy something like BGP, EVPN, as a control plane, and using VXLAN to create those overlay segments on top of routing layer 2 over layer 3. But NSX-T solves that with its own way of overlay networking using Geneve encapsulation. And Geneve encapsulation is just another way of tunneling layer 2 over the top of layer 3. And what that allows you to do is no matter the placement of those pods for those applications you're running, they will, so long as they're a part of the same namespace, they will be a part of the exact same subnet, regardless of where they live inside of your data center. So that gives you that ability to scale out, scale in your applications. You're not confined to a single, you can call them availability zones within your data center. NSX just provides that overlay networking to facilitate that from happening. So just to recap on this slide here, NSX-T is our software-defined networking overlay or solution that we're using for Kubernetes, as well as anything else we have in our data center. It's going to interact with the Kubernetes CNI, or the container network interface, in order to be conformant with Kubernetes objects. So more specifically, what does this look like from a Kubernetes exclusive perspective? So from left to right, if we're looking at it, first, how does this actually work? So how this is all pulled together is using the NSX-T container plugin, or NCP. So what this means, if I'm looking at that little graphic there, we have a user, we have some sort of Kubernetes administrator, and they're going to create a new namespace, or create a new pod, or create whatever object they're attempting to create in Kubernetes. So maybe that might be a network policy, a deployment, a service of type load balancer, an ingress, all those objects that typically rely on your network infrastructure. And going back to the benefit of Kubernetes is that in your application definitions, you incorporate what the infrastructure is going to look like as well. So we're no longer building applications and then hoping that the network or the physical infrastructure will actually support the application. Now, when we're building our Kubernetes manifest, we're actually building the application infrastructure into it. So they're closely combined. And that kind of brings about that whole idea of DevOps, right? You have your developers building their applications, operations engineers supporting the physical infrastructure, the software-based infrastructure, and Kubernetes is a good way to tie those two things together. So when you have an application and you deploy those manifests to Kubernetes, the Kubernetes API is going to consume those objects, and being a desired state configuration model, it's going to say, okay, this is what your desired state is. And this example will say your desired state is to have a service of type load balancer. So you need an egress IP address or an external IP address for people to access your application. It's going to interact with NCP, the NSX-T container plugin, and that plugin is actually going to translate that object into an API call into the NSX-T control plane to actually realize those objects, and then report the realization of those objects back to the Kubernetes engine to then ensure that control loop is succeeded. So to recap that, when you submit a Kubernetes manifest like a load balancer, it's going to interact with NCP, and that's going to translate into NSX-T API calls. And then NSX-T is actually going to build out a physical load balancer, or a software-based load balancer for your application, assign it an IP address using IPAM and DHCP and things like that. and go ahead and report back, here's your IP address, here's your service type load balancer, all dynamically without you having to actually know anything about NSX-T from the perspective of the Kubernetes administrator. And that goes along with any other object as well, such as ingress controller, network policies, and we'll take a look at that in just a second. The second part that's unique to NSX-T and how it relates to Kubernetes is the actual topology that you're getting out of this. So this isn't deploying a topology where, for example, you have a subnet per node, and everything's kind of exclusive in that way. This builds out a logical topology that incorporates routing and switching in the solution as a whole. So when we're looking at this from a top-down perspective, we see here we have T0, active, and a T1 per namespace. And then below that, we have all of our pods that are running on the various namespaces with their firewall attached to the actual pod itself, as we talked about previously with the distributed firewall. So what this means is that for each one of your namespaces that are deployed, you're going to have a dedicated T1 router. So that allows you the ability to efficiently segment off all of your namespaces, not only from the compute perspective, but also the network perspective. So if you think about namespaces from an isolation perspective for multi-tenancy, you think of it as a namespace is a way to carve out compute resources on a single host dedicated for your resources. Well, that doesn't typically incorporate itself into the network, right? So typically you can have all of your same namespaces, but they're still going to use the exact same logical network topology. So the same routers, the same things like that, because they're all going to be, most solutions today are host-based. Well, NSX-T implements a routing architecture that allows you to have each one of your namespaces are not only segregated by the compute resources on the hosts themselves, but it's also going to create a completely dedicated logical network fabric for that namespace to traverse. So you have layer 3 points where you can invoke policy from a north-south perspective per namespace, as well as your distributed firewall that's going to be located on each pod, which are realized through network policies in a Kubernetes terminology. So this really just gives you a whole nother layer of isolation. And that goes along with that same idea of incorporating the application into your infrastructure. This is just another way to incorporate the application and your multi-tenancy idea of having namespaces into the network fabric itself. Again, it's all done programmatically. It's not something you have to set up manually. When a namespace is created, NSX will go ahead and create a load balancer for that namespace. It'll create a layer 2 segment for that as an overlay, and it'll create all the NAT policies that are required specifically for that namespace. Next, we have network observability. So this is something that obviously there are tons of solutions out there to view the traffic flow of your pods and insights and things like that. This is something that is just coupled with NSX-T. There are several tools that are incorporated, and some are directly integrated inside of NSX-T for visibility into your pod-to-pod traffic, as well as pod to external traffic. So we'll take a look at one tool that's built in there called TraceFlow, and we'll be able to use that to actually very granularly see exactly the path that our pods are taking, what physical nodes they're taking, what firewall policies, what NAT policies they're hitting as they traverse the environment. And that helps us troubleshoot for issues, things like that. But there's also tools like vRealize Network Insight or NSX Intelligence that actually use machine learning to dynamically ingest all of the pod traffic using IPFix or NetFlow, establish known flows for pod-to-pod traffic or pod to external or external to pod traffic, and understand what is an acceptable use case, or what is an acceptable or common baseline for application traffic in your environment. You can use something like NSX Intelligence or vRealize Network Insight to understand what is actually talking to what in your environment, and then use that to create a security policy. So once we know exactly what is supposed to be talking to what, we can take that information to create a whitelist security policy to only allow known good traffic and have everything else dropped in the environment. And that's how NSX works out of the box, especially with Kubernetes, is that only traffic allowed is traffic that is assumed to be known good. Every other piece of traffic is going to be dropped. For example, namespace to namespace traffic is not allowed by default in NSX-T when you deploy to Kubernetes namespaces. They will have their own dedicated T1 routers, and there won't be there won't be a policy that explicitly allows communication between the two. So all that traffic is going to be dropped. And you can use something like NSX Intelligence or Verni to go ahead and identify those traffic patterns and build policy to support them. The last step here is NSX-T provided services. So NSX-T is not just the network overlay. This is kind of a reiteration of what NSX-T is in general and how this conforms to Kubernetes. So we have distributed firewalling, which is going to be that object type of network policy. We have load balancing provided by this. So we have an on-prem load balancer or service type of load balancer, as well as a layer 7 load balancer if you're using something like an ingress controller. It also supports dynamically everything you'd expect, such as HPA or horizontal pod auto scaling. As your pods scale out in those server pools behind a load balancer, NSX completely supports that and will handle it dynamically at the time of scale in or scale out. So this just provides you that a lot of those capabilities you would expect to get out of a public cloud resource and puts it on-prem for your applications to consume. So when you're building out your environment and you have an application that is supported on a VCF or a VCF with Tanzu cluster basis, that application becomes very, very portable because you're not doing anything specific to VCF. You're building your applications just as you would do in any other cluster around the world, any other platform. So it gives you that, building this out gives you that cloud native architecture, that ability to have portability and scalability to your applications. Okay. So that is the slide part of it. And now let's jump into the UI. And I just want to walk through over the next 10 minutes, walk through what the environment looks like and just kind of play around with it for a little bit. So I'm logging into my VCF environment and I have here a workload domain vCenter. So when I jump into this vCenter, I see I have my physical hosts. I can see that these hosts are actually running Kubernetes. So these are all acting as Kubernetes worker nodes. So I have the 3 controllers here, and I have 4 actual worker nodes, which are my bare metal ESXi hosts. And then I come down here and I have this concept of namespaces. Now in this concept of namespaces, this is the vSphere with Tanzu kind of place where workloads are scheduled. So in here, I have a few different namespaces. I have one that's NB Tanzu, NSX-T, and then I have the integrated harbor registry. Then I have these 3 virtual machines, and these virtual machines are the actual Kubernetes control planes VMs that are managing and scheduling all these different workloads. So if I take a look into these different namespaces, I can see that I have different types of objects in here. So in this NB Tanzu one, I have my objects that are my vSphere native pods. So I have a few pods that are running directly on ESXi using that CRX container runtime. But I also have a Tanzu Kubernetes grid cluster, Tanzu Kubernetes cluster in here as well. So I have a separate Kubernetes cluster that if I needed to run specific services or things that are ran server side, I can do that here and have that more CNCF conformant Kubernetes cluster deployed if you need something more advanced that you couldn't do with the vSphere native or vSphere pod service. So I have all these objects. They're organized by pods, and when I are organized by namespaces, when I jump in here, I just have this different visibility of how this actually looks and how to manage this. But this isn't a talk that's focused about this. It's focused on NSX-T. So I just wanted to set this framework of this is what my infrastructures are actually running, my pods and my different clusters. This is how it looks if you've never seen vSphere with Tanzu. But let's go ahead and look at what it looks like from an NSX-T perspective. So here we are in the NSX-T dashboard, and this is just that single pane of glass type speak for all of my network policies for, again, bare metal, container, VMware, virtual machine, anything like that. And let's go take a look at the inventory. So I can see NSX-T does have an inventory. It is integrated with my Kubernetes cluster using that NSX-T container plugin. Because it has that context awareness through vCenter, I can actually see exactly what's running in my different namespaces. So if I look at here at the NSX-T, I can see I have my 4 Yelp pods running. See the IP addresses that NSX has given to them and what services are actually associated and what labels are associated with them. These labels are actually quite important because I can use these labels as I instantiate my Kubernetes objects to then, because NSX-T is aware of these labels, I can then use these to invoke policy upon. So I can create groups that say all containers or all objects that have a tag of application A, put them in this security group, and then apply security policy to that. So as you scale in, you scale out your application. Say you scale out your Yelp UI, and you have a tag on this that says, application Yelp. as this Yelp UI scales out, it'll be dynamically added to that group, and security will then be placed on those new objects. So it all happens automatically and dynamically, and you don't have to actually go in and know the subnet of this and create firewall rules for the subnet or anything like that. So we see that it has inventory, it has visibility into what these clusters look like, where these pods are living. But let's see what the network topology that it actually built out for us. So this view gives us a good little insight into what actually is going on. So we see, kind of like diagram earlier, I have my T0 gateway that's actually connected through BGP to my top of rack switches. Through that, I have all of my logical routers and my T1s. And these T1s are then, see, I have 7 T1s here, and each one of these T1s map to a namespace in my environment. So each one of these T1s are a dedicated layer 3 gateway for each one of my segments that are directly mapped to a namespace. So we can see here that I have, I have VMs, I have pods, and let's find one that has pods in it. We can see here that I have these 2 pods that are running on this segment through, this T1 going out to the T0. And I can invoke services at this T1 here, or invoke security at this T1 here, or at the pods themselves, because they are running the distributed firewall that has, that stateful firewall capability directly on the pod interface, kind of where my mouse is right here. So I have several points for visibility and several points for security invocation. So we can kind of look around at the different load balancers. The same thing goes for each T1. For each namespace is allocated T1. Each namespace is also allocated its own load balancer. So we can see that I have a load balancer here that is dedicated for that NSX-T, another one for the MB Tanzu, and then I even have one for those other clusters that I deployed. So this is for the actual cluster itself. And we also instantiate all of our cluster IP objects as well in a distributed load balancer. Okay, so let's look at some of the, first of all, let's look at some of the visibility stuff that we can get out of this. And I just wanted to show the tool Traceflow. And we'll do this first. I'll implement a rule, and then we'll go ahead and check it out. So let's look at one of my applications, and I just happen to know that it has this tag on here. If I spelled it right. So we'll look at this. This is a pod that's running in my environment. So NSX-T has, visibility into what that actually looks like. And we can take a look at what does it look like if it's going over to my Yelp UI. So can this pod, they're in different namespaces, can they reach each other? And what does that traffic flow actually look like? And where do I have my opportunity to invoke security? And where's that visibility actually sitting? So as this runs, this takes a little bit, and what it's actually doing is injecting synthetic data into the actual transit path that's required for this. So this isn't just going to simulate, this is actually going to inject traffic. So you can see exactly from start to finish where this traffic flow is going to go from pod go figure to pod Yelp UI. So we can see it goes through all these different processes. It goes through my distributed firewall. You can see what actual rule ID that it hits. You can see what segment it's going to be routed on, the T1s that's going to be routed. Then you can see it actually hits my physical network, and it goes to my edge nodes, where it's actually being, that's where it's actually all the services are going to be imposed. So this is where I have my north-south firewall. We can see that crosses it here. We can see where I have NATing taking place because it says between namespaces. And then finally, we can see down at the end that this is actually blocked by a firewall rule that is the firewall ID 1005. Without looking at it, I can tell you that that is the deny all at the end of the list. And that's because this traffic flow wasn't explicitly allowed. I don't have any reason in this topology to allow namespace to namespace traffic. So it's not allowed, and therefore NSX is going to go ahead and drop it. But if I were curious, why isn't this traffic working? I can use this tool to have complete visibility of exactly where this packet actually went from pod to pod perspective and where it actually failed. So now that we know exactly what the traffic is doing, what rule is failing it, let's try to fix this, because say we do want that traffic to work. So let's go ahead and take a look at security, and we're going to focus on the distributed firewall here. So the distributed firewall, again, is the east-west firewall, where each one of these policies are actually built out directly on the pod themselves. So when the pod, any traffic that egresses that pod is going to be scrutinized by this security policy. If that traffic is not mentioned here as allowed, it explicitly allowed as known good traffic, it will be dropped. So we can see that automatically it creates quite a few different rules, for my namespaces themselves and allowing egress access, but there's no access that is allowing from this namespace to this namespace allow that. So there's different ways to accomplish that. So it depends on what hat you're wearing or what role you are in this different environment. So from the perspective of an operations engineer, I would have access probably directly to NSX-T. I can go in here and create this rule, publish it based on the different groups of my application itself, and call it a good day. However, if I am an application developer or Kubernetes administrator, I don't necessarily have access to NSX, or I don't want to learn NSX. It's just another thing that I have to tack on. It's not part of my direct skill set. So I want to use Kubernetes. So say I'm in from the perspective of a Kubernetes engineer, and I'm going to log in to my Kubernetes cluster, and I'm presented with all the namespaces that I have access to. And so I'm going to actually log into my NSX-Sec namespace. Okay, so let's just do a quick, let's get nodes to see, we just kind of get the lay of the land we're looking at this from a Kubernetes perspective. So, okay, so I have all 4 of my, my actual worker nodes, and I have all of my control nodes as well. So that's good to go. Let's see what pods I have running. So we can see that I have my Yelp application running. And let's see what services are actually running for this. And we can see that I have a service type of load balancer with an external IP address. And this external IP address is actually located on NSX-T, and it's realized in one of those load balancers that we just took a look at. So let's do this now. Let's see. I want to be able to allow that other namespace into my Yelp UI. I want that traffic to actually flow through. So if I look at network policies, I see I don't have any. So I don't have any network policies in here. So what I'm going to do I don't have access to NSX-T, but I do know that I can build out some policies because I know what my application needs to do, probably more so than the operations engineer in a lot of cases. So being a network or an Kubernetes administrator, I'm going to go ahead and create this object of type network policy or of kind network policy. What I'm doing here is just matching labels. So I'm matching my app labels of Yelp UI, which in my Kubernetes manifest for that is the label that I give that specific service. For all traffic ingress, I'm going to match. So this is essentially just allowing all traffic ingress into my pod from the namespace that has this label. And this namespace is actually saying all namespaces in my environment. So I'm actually allowing all namespaces access into my Yelp namespace. So what I'm going to do is apply that just like as I would as a normal Kubernetes administrator. Okay, so I applied that, and let's go ahead and just make sure that it was realized. Okay, so I have my network policy built out in my namespace. So ingress traffic can hopefully flow into my environment. So with that, I didn't need to know anything about NSX-T. I didn't need to know any of that other stuff about networking. I know that I create this object. When this object is sent to the Kubernetes API, it will send that to the network container plugin, and then it will translate that into an API call to NSX-T, which if we go back over here and refresh this, we now see another rule set here. So NSX-T went and created this rule set based on that network policy, allow ingress, all ingress allow, and we can see that it created these groups. So it created this group as a source, and the source is all the IP addresses in the other, sorry, this is probably easier. These are all the different segments that are created for the other namespaces. So now this is the group that's created. So anything that shows up in these segments is going to be added to this group and allowed into my, as a destination, into my Yelp UI. And in here, I only specified that one application, that one microservice. And so it only has one IP address here. But if I were to scale that service out to say 10 replicas, it would dynamically add each endpoint that is a part of that replica set, or that service type load balancer will then be added here as well. So that my security policy right now that's allowing any traffic into it will be realized across the scalability of my application. So just to prove that, if we go back over here to trace flow, and we can actually retrace the same one. And what we should see is that now, because that traffic is actually explicitly allowed, because the application administrator needed it to be allowed, now we should be able to see that that traffic is now flowing through the environment and actually succeeds as it goes through. So let's hope that it does. And we see that it was actually delivered. So down here at the bottom, we can see that it did cross this firewall rule. And if you look at this firewall 3061, before it was allowed to actually hit the thing. So let's go look at what is firewall rule 361. And I'm just going to search it up here because I don't feel like digging around. I can see firewall rules, and then here we go. That's our actual rule that we just created, the all ingress allow. So that rule is now used across our environment. And that just gives us really deep visibility and being able to test what's actually going through and define the flows in our environment. And that was just a really simple example of how we can use NSX-T as the software-defined fabric for our virtual machine, as well as our Kubernetes fabric. So to end that, this is just a quick summary slide that NSX-T overall is an overarching network fabric for supporting your entire software-defined data center. That includes Kubernetes, containers, VMware, workloads. You can run NSX-T with Linux transport nodes as well. And overall, it provides that seamless use case from your operations engineers who are familiar with that type of infrastructure, as well as your Kubernetes or developers engineers who are going to be consuming it from a different perspective. So I hope everybody enjoyed that and got something out of it. But that's all I had to show here today. So I thank you guys. Thank everyone for joining. And if there's any questions.
Yep, we do have one question here. It says, can NSX work with other Kubernetes environments outside of Tanzu?
Yes, absolutely. So that NCP or the NSX-T container plugin is, it's not specific to Tanzu. There's nothing that is unique to Tanzu with that. And so it's not as automated to deploy it. For example, in my VCF environment, all of that was done on my behalf. It was automated through the deployment of Tanzu itself. But if you have OpenShift clusters, if you have vanilla Kubernetes clusters, you can deploy that NCP, integrate it into an NSX-T deployment, and you can have a lot of these same benefits. Again, it's really just that intermediary NCP it's going to be running as pods. So it's running as pods on your cluster, and it's just translating those Kubernetes objects into NSX-T objects to facilitate load balancers, firewall rules, and all that good stuff. So no, there are white papers out there that you can use NSX-T with things like OpenShift and other solutions as well.
Great. Thanks so much, Billy. That's all the questions we have for today. Thank you, everybody, for joining us. If you do have any follow-up questions, please don't hesitate to reach out to any of the email aliases you see on the screen. We did record this session, so if you would like the recording of it, please also don't hesitate to reach out to any of those email aliases and we can make sure to get that to you. Have a great day.